everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over more molecular orbital energy diagrams involving homonuclear diatomic molecules. And specifically in this video we'll be focused on alkali metals and alkaline earth metal molecules. So let's get into this. So first thing I want to talk about is that so far in these videos, we've been focused on the valence electron, valence orbitals, and not so much on the inner core orbitals. And there's a couple reasons for that. One is that the valence electrons are farthest from the nucleus. And so when the two atoms come together and those orbitals overlap, they by and large don't really perturb the inner orbitals all that much. That's the first reason. So those inner orbitals don't become really involved in the bonding or the forming of molecular orbitals all that much. That's the first reason. The second reason is that all of those inner orbitals that are not valence are going to be completely filled. And what that means is that you've got an equal number of bonding orbitals and anti-bonding orbitals such that the bonding order, when you add all those together, is going to be zero. We saw that before. So for example, if you have the ns, sigma ns, and the sigma star, this would be tied to the 1s orbitals, right? So if this gets all filled up, this would be like your core electrons, your valence electrons, right? So if I fill both of these in, I get a bond order of 0. And then if I have more electrons, I would fill up next higher orbital, and then I would have the valence electrons over here if this was considered core, right? So this would be like the 1s, and you got the 2s, and then you got the 2p, and so on. This is just involving the 1s. So when you get the 1s together, you get your sigma bonding and your sigma star anti-bonding. If both of these get filled up, you got a bond order of 0. And then if you add more electrons, this becomes core. And so then we don't have to worry about this because this is all filled up and complete, and it gives us a bond order of 0. So that's going to be the same for all inner core filled electron valence shells, or I'm sorry, electron inner core shells that are not valence, that are closer to the nucleus. Okay, so those are a couple reasons why we are focused only really on the valence orbitals. So again, as I said in this video, we're going to be talking about the homonuclear diatomic molecules that involve alkali and alkaline earth metals. These are the first two groups, groups 1 and 2 in the periodic table. So if I show you quickly on the periodic table here, so you'll see that these two groups on this side, on this side over here, these two groups here. So we got group 1, and then we got group 2. So group 1 right here, I'm getting confused. Group 1 here is your alkali metals, and then group 2 here is your alkaline earth metals. Notice that both groups are in the S block. So these only involve the S orbital as their valence orbitals, right? Because those are the S orbital is the only one that has electrons in it when it as concerning the valence shell. So sorry, I'm getting tongue-tied. Okay, so that's why we have here the NS. N refers to the first quantum number, the principal energy level, 1, 2, 3, 4. And so since the alkali metals are in the group 1 elements, that's going to be, they're only going to have one electron in their S orbital, right? So depending on what period the element is in, that'll determine what N is, right? So if we have lithium here, then that'll be N equals 2. If it's potassium, then it'll be N equals 3. So this will be 3s. So, but it doesn't matter what energy level it is in because it behaves all the same. So because they're all in group 1, they all have the same number of valence electrons. So the orbital diagram, the molecular orbital energy diagram will be filled in exactly the same way. So for alkali metals that form a molecule, a homonuclear diatomic molecule, meaning homonuclear, meaning that it's the same type of atom being bonded, and then diatomic means you have two atoms. So two atoms of the same homonuclear diatomic molecules. So for your alkali metals, it would be Li2, Na2, K2, rubidium Rb2 or CS2. And so the way this works, just like before, same thing with hydrogen and helium that we did in the previous videos. The metal, one metal has one electron. So if this was lithium, we'd have a lithium metal with one electron in it in the s orbital. And then we'd have another lithium atom with an electron in its s orbital. And then we combine those two atomic orbitals to form the molecular orbitals of M2. M represents the metal. In this case, the metal is an alkali metal. So either lithium or sodium or potassium or rubidium, one of those. So the way this works, again, is the one electron, we have one valence electron in the s orbital. So that's going to be one there for this metal atom, and then one there for that metal atom. We bring these together to form the molecule M2. And so these two valence electrons are then going to fill in the orbital diagram, the molecular orbital energy diagram here. So we're going to put these first into the lowest energy level, molecular orbital. And so this is going to be filled with 2. We only have 2 electrons, so those 2 electrons are going to go into the lowest energy level, and nothing goes into the sigma star energy level. And if we calculate the bond order here, the bond order is going to be equal to the 2 bonding electrons minus anti-bonding electrons, which is 0, divided by 2, and that gives us 1. So we would expect or predict that all of these, lithium 2, sodium 2, potassium 2, and so on, are going to form a single bond between them. And from our experimentation, from our data, we do see that these all exist in the gas phase, and some of them even might exist in the solution phase as well. And next we go to the alkaline earth metals. Same setup. The only difference between the alkali metals and the alkaline earth metals is that, well, because the alkaline earth metals are group 2 elements, they all have 2 valence electrons in their s orbital. And so what would we expect to find when we try with regard to the formation of beryllium 2, magnesium 2, calcium 2, or strontium 2, or barium 2? Are these going to be stable species? We just saw that the bond order for these is going to be 1, so these are going to be stable species, right? Like as I said, these all exist in the gas phase, and some of them exist in solution. What about these? What would we expect for these? Again, the atomic orbitals of each of the metals has 2 valence electrons. So we have 2 valence electrons in the ns orbital for our metal. So here's a metal atom with 2 valence electrons in the ns, and here's the other metal with 2 electrons in the ns. And again, they're the same atom. So for Be2, these would be both beryllium, Be and Be. If it was magnesium 2, this would be magnesium, and this would be magnesium. This applies to all alkaline earth metals. So you see here that since we have two valence electrons in this atomic orbital and two valence electrons in that atomic orbital, we're going to have a total of 4 valence electrons to fill in the molecular orbitals. So now we have 2 electrons go into the lowest energy molecular orbital, the sigma ns. And then we have 2 electrons left over. They're going to have to go into the antibonding orbital, the sigma ns star. So then when we calculate the bond order here, again, the number of bonding electrons minus the number of antibonding electrons. This time we have 2. And we're going to divide that by 2. 2 minus 2 is 0 over 2, which gives us 0. So the bond order for these molecules is 0. So none of these are going to be very stable at all. None of these exist in gas or solution. Beryllium Be2 will exist at very low temperatures. But all of these are really going to exist as metallic substances with the sea of electron bonding them together as solids. So these are all going to exist as solids, but as a lattice structure of atoms in a sea of electrons according to the sea of electron theory or model of metallic bonding. But these are not going to exist as molecules, Be2 or Mg2 or Ca2 as either, in any state. So that is an overview of the molecules and the stability of the molecules for your alkaline and your alkali metals and your alkaline earth metals. I hope this was helpful. If this was helpful in any way, if you enjoyed this video, then please by all means like the video, share the video, hit that like button somewhere over here. Also, make sure that you subscribe to my channel. Help me out here, please. Okay, so make sure you click on that the notification bell. When you do that, click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.